So welcome everyone here and online to the Mobile and Wearable Health Seminar Series. The speaker today is Yuzhe Yang, is an assistant professor in computational medicine and computer science at UCLA, but he is also a visiting faculty researcher at Google. So thank you for being here in person and online, and the floor is yours. Thank you.
Yeah, thank you, Cecilia, for the introduction, and thanks everyone for being here. So actually, this is the first time to Cambridge, UK, but I actually spent 6 years in Cambridge, US, so it's really nice to be here. Okay, let's get started. So to just motivate my talk, I'll make a claim. So our human are infinite data generator. So across seconds, our body generates continuous and dense physiological signals, such as your EEG and EOG, your cardiac signals, such as your heart rate, your ECG, SpO2, and your breathing signals like respiration from your thorax or your abdomen or even airflow, as well as other signals such as continuous glucose or EMG and even IMUs. So the question is, because we are generating these signals every second, every day, continuously, but we don't have such an intelligence layer that can help us to interpret and provide actionable insights for all these kind of signals across timescale, frequencies, and domains. So fortunately, today, we have a huge amount of personal devices and sensors around us. And these sensors, like smartphones, smartwatches, or even like smart rings, they passively collect our personal data. And even we can say it's almost 24/7. So what if we can turn these everyday devices into this intelligent layer that can help us to understand our human, help us understand our health more effectively and provide actionable insights? So let's imagine using these devices, using these everyday devices with AI power. And what if you can get your physiological vital signs, such as your breathing, your heartbeats, or even your SpO2, but just looking at your smartphones or laptop without any physical contact? And what if these smart devices can further do complex disease diagnosis based on these common physiological signals? And what if this can be done even before the actual clinical diagnosis happen? And further, what if these at-home AI devices can further track your disease severity and progression across time in a continuous manner, and further identify your medication response and help you personalize and adjust your medications in real time? So this is exactly what our lab at UCLA is doing. So our lab is called Health Intelligence Lab. And the first pillar we're working on is to build multisensory foundation models and agentic AI that try to understand this everyday data, spanning from sensor data, wearable data, sleep data, and to build this personal health agent layer to try to understand them. And to make these models more deployable and reliable, we also work on frontiers to try to enhance its transparency and interpretability to make sure we can actually deploy these models in real clinical settings. And built upon these models, we try to use these everyday signals, sensory data, plus AI to help drive scientific discoveries in human health, including identifying biomarkers for neurological diseases, such as Parkinson's and Alzheimer's, and to identify insulin resistance, which is a precursor for type 2 diabetes, and also try to identify populational fairness and potential biases induced by these models. And in turn, we also try to make these models deployable on these everyday devices so that it can bring accessible healthcare to consumers and to people in the world. And this span over physiological sensing using smartphones and also in-home tracking of personal data and their disease progression using contactless devices, and also spanning broader medical domains.
Still can use that target rapidly. Okay. Yeah, that's good.
So any questions in the audience? Okay, so I'll just move on. So in this talk, I'll basically introduce three parts of our recent research that is building foundational and agentic AI for understanding human physiology towards personalized healthcare. So the first part, I'll briefly introduce why sensing these continuous physiological signals are important. And I'll give a concrete example. So in this case, we developed an early detection biomarker for Parkinson's disease. Just use your daily breathing data. And then we'll go beyond to this specific disease to illustrate how we can build foundation models for human sleep that can go beyond a single disease, but provide a foundation encoder that can be adapted to many cohort studies and adapted to many diseases prediction. And finally, I'll briefly touch our recent work on questioning or validating whether LLMs or existing multimodal LLMs can really reason over these dense physiological signals and what's the implications for the field. Right, so let's dive in. So this paper I'll start it is on early diagnosis of Parkinson's disease with our daily nocturnal breathing signals. So we all know Michael J. Fox. He's one of the well-known and famous TV show and movie star with his famous Back to the Future series. So here's an interview video by Michael. And from this video, we can clearly see his irregular body movement and his hand tremors. And in fact, this is because Michael was diagnosed with Parkinson's disease, or PD in short. So what is PD? PD is the fastest growing neurological disease in the world. And over 1 million people in the United States and 10 million people worldwide are living with PD as of 2020, which results in an economic burden of $52 billion per year. However, a key difficulty in Parkinson's is that we cannot diagnose it in time. So in clinics, the disease is typically diagnosed based on motor symptoms, such as tremor and rigidity. However, these motor symptoms often show up many years after the disease onset. And by the time a clinical diagnosis is made, the disease has already been progressed for decades, and this will cause non-reversible changes to the human brain. So the challenge here is not just to diagnose Parkinson's based on these motor symptoms. The real goal here is to have the foresight to detect the disease early on, even before anyone has any clinical signs. And people have thought about how to develop such a biomarker. And over the years, researchers have studied CSF, neuroimaging tests, and blood biochemical evaluations as potential biomarkers for PD. Well, these markers have shown pretty good diagnostic accuracy in terms of what you see on their specific cohorts. They have some straightforward drawbacks. So they're invasive, they're expensive, and they require specialized access to these clinical medical centers. And as a result, they could hardly diagnose disease in the early stage. So we asked ourselves, could we develop a biomarker that is easy to measure in a daily at-home setting and can be repeatedly measured across time, while also match the same level of accuracy as these clinical methods? So the answer is yes. And in this project, we have developed an AI-based system that analyzes your nocturnal breathing signals. And this results in an early detection biomarker for Parkinson's. So the first question is, why? Why nocturnal breathing? So the connection between Parkinson's and your breathing or even your sleep is noted as early as in the first draft published by Dr. James Parkinson, who discovered this disease. So he observed in his first cohorts of patients the connection between sleep, breathing, and Parkinson's. And clinically, it is also observed that early stage Parkinson's can show changes in their brainstem area that affect breathing. And researchers have also shown evidence on sleep breathing disorders on specific PD cohorts. And more importantly, monitoring the breathing is very simple. It can be done every day in an at-home setting. It is non-obtrusive, and we show that it can actually match the accuracy of all the clinical methods mentioned before. So here's how our system works. We capture breathing data either by wearing a breathing belt on chest or uses a wireless device that transmits wireless signals and collect the reflection to derive the whole night breathing signals. And with either method, we're able to obtain a full night of nocturnal breathing signals with high quality. And after capturing the nocturnal breathing, we then design a dedicated AI model to extract disease information directly from the data. So the model has two outputs, whether the person has PD or not. And if they do have PD, we'll also estimate their disease severity with respect to the clinical gold standard measure, which is a continuous score. But how did we build it? And in fact, we identified several key challenges. First, the input nocturnal breathing signal is high dimensional with tens of hours, whereas the output about the disease is extremely sparse. So we're essentially trying to infer this one bit of information for PD from a very high dimensional and dense input. So this sparse supervision poses a risk of overfitting, which is a very classic machine learning issue. And where this network or this model may pick any random spurious correlation in this high dimensional and dense data to fit this objective, while it learns nothing related to the disease itself. So the key question here is, how can we regularize the model training to make it learn the PD information effectively? So our solution is inspired by the link between Parkinson's and our brain activity, as PD is a neurodegenerative disease. And in fact, when we go to sleep, our brain activity fluctuates throughout the night, which can be quantified by our brain EEG signals. So based on different frequencies of our brain waves, we can divide EEG activity into 4 frequency bands, and from low to high, they call delta, theta, alpha, and beta bands. So different EEG activities are associated with different physiological functions of the brain, which naturally provide evidence for Parkinson's. And now we can take a step back. You might wonder, because we're talking about nocturnal breathing all the day, and now what's the connection between breathing and EEG? So we show that by just using your nocturnal breathing signal, you can actually reconstruct your EEG throughout the night with pretty high accuracy. And as you can see here, as an example, the orange line is our prediction, and the green line is the ground truth. So it basically captures more than 90% of the correlation. So this tells us that such a prediction task from nocturnal breathing to predict EEG can naturally serve as a dense supervision for the model training. And specifically, instead of directly predicting the disease information, we add another prediction branch to directly predict this brain EEG activity from breathing signal. And this essentially forms a multitask learning framework, and where this EEG prediction serves as an auxiliary task to provide additional supervision for the model training. And indeed, by integrating this auxiliary task, we see substantial improvement on the diagnostic accuracy from chance level to an impressive 80% accuracy. Okay, so there are still other algorithms we propose to make it more robust, but I will skip those details, but happy to talk more. And I will just show you the main results we get. So to evaluate this system more broadly and make sure it actually works, we create a very large data set by collaborating with many different institutions. And in total, we have over 7,000 individuals with over 700 PD participants. And with our AI model and all these customized algorithms, we can achieve pretty high diagnostic accuracies across different institutions. And note that here, each bar means we held out testing, which is we held out that institution's data during development, and all the data are unseen. And we directly test that data once the model is developed using other data sources. So the model shows pretty robust performance across different institutions, as well as across different sensing modalities. So the most interesting part from this project is that the model also shows initial evidence for early diagnosis. So in our dataset, we identify a group of patients who were diagnosed with PD in the clinic 6 years later, but they were not diagnosed 6 years before. And we do have data from the same participants over these 2 clinical visits. So what we did is we directly test model on this visit 1 data. And first, we collect age and gender and other comorbidity matched control subjects from the same visit and show that, okay, the model can correctly identify them as controls. And further, when tested on this prodromal PD group, the prediction score of the model actually is statistically significantly higher than the control group. And this shows that the model is able to provide earlier insights on this specific group. And we do need to acknowledge the limitation that the number of participants here is small, because this essentially is still a chicken and egg problem, especially on retrospective data. But this will have broader implications for how you can choose participants to enroll in drug clinical trials. So another advantage of this system is that it can also detect the severity of Parkinson's with high accuracy. So here we show each dot here is 1 participant, and the x-axis here is the clinical gold standard measure of PD severity, which is called the SUPR score. And the higher the score, the more severe the disease is. And the y-axis here is our model prediction. And we show this prediction actually have pretty high correlation with statistical significance. And here's the exciting part. Once we can evaluate the severity of the participant, and by monitoring breathing every day at home, we can actually track the disease progression in a very fine-grained manner. So let's say a patient we monitored for over 1 year. So here, also first, traditional clinical measure of PD severity is usually done every 6 months. And we show here the baseline measurements, the month 6 measurements, and the month 12 measurement. And as you can tell, they're basically very sparse. And on top of that, they also exhibit very high variance. For example, the score here at month 6 is significantly deviated from the baseline. And we know this is impossible because Parkinson's is non-reversible. And this is very likely due to the subjectivity of the clinician, as well as the measurement noise during that clinical visit. And now let's take a look at these predictions from our AI model. So our approach offers more robust and frequent measures of the PD severity, and this provides a much clearer path for the evolvement of their disease scores. So this could let us understand the disease progression in a more fine-grained manner. Okay, so I will slightly pause here to see if there's any questions for the first part.
I have a good question.
Go ahead.
On slide 22, it was not clear to me what the control group was. Was it like people that didn't have Parkinson's and that you tried, you tested if your model predicted them as Parkinson's or not?
So yes. So the question is for the control group, how do we select them?
Yes, exactly.
So for the control group, we first identify this prodromal group based on their clinical EHR.
Okay.
Were diagnosed in this time, but not this time. And then from the same visit, we select control subjects who do not diagnose for both of the time. So we assume they will not develop Parkinson's. And then we select we basically match their comorbidities, like the same age distribution, same gender distribution, etc. So this is how the control group is selected.
Okay. So the model still probably, my understanding, to some degree mislabels some users that do not have Parkinson's as having Parkinson's.
Yes. So basically here, you can read this as the threshold we classify PD or not. I think you're right. So from this figure, you can also calculate the sensitivity and specificity, which I believe will lie between 0.8 and 0.9. So yes, so we still misclassify some of them. But I think the takeaway message is there's early evidence that we can classify them further.
Yeah, so thank you. Very interesting.
Yeah, thank you.
So you reconstruct the EEG from respiration, right?
Mm-hmm.
But what's the reason for it? I mean, I got it that both from respiration and EEG, you can see and detect some kind of inflammatory to the Parkinson. But is there like a physiological reason why you can reconstruct EEG from the respiration? I'm a bit ignorant about this.
Yeah. So the question is there any physiological groundings that we can reconstruct EEG from breathing's input? The short answer is no. So, well, I shouldn't say this. The short answer is yes and no. So there's no existing, like we did this work in 2022. So at that time, there's no existing established medical literature that explicitly studied this. But physiologically, because your breathing and EEG are both modulated by your brain, so they should share correlations in principle. And what we did here is we try to use a data-driven method to discover this correlation and to what extent they are correlated. So to further add on that point, is EEG is actually highly correlated with Parkinson's because there are existing established literature look at the EEG distribution and how they are differentiating between PD cohorts versus control cohorts. So that's why we are picking this EEG data as our kind of like intermediate proxy modality. So there's reasons like why we choose this, and there's reasons why we put it on the output side instead of input side. Thank you.
Sorry, can I have a follow-up question?
For sure, yeah.
On the slide, yeah. I understand that in sleep we have different stages. So when you are doing this reconstruction of the EEG signal, is there any specific stage that's particularly useful or particularly not useful?
Yes, good question. So the question is there any interesting behaviors with respect to sleep staging and for prediction? Yeah. So actually, I had this slide I prepared for such questions. So so basically, what you can do once you have this model is, I didn't touch the interpretability part, but once you have this predictive model, you can reverse engineer it and to see, okay, what part of breathing actually drive the prediction. And as the question mentioned, like we can also plot not only our breathing signals, but also the corresponding sleep stage. And we also visualize and inform our attention score. So what is attention? So our model is actually a deep learning model, and you can visualize, okay, so so the attention is just a mechanism that tells you which part activates the prediction the most. So you can basically view this as, okay, this part and this part is activating the prediction for control. And this part and this part is activating the prediction for Parkinson's. So we do observe differences between Parkinson's and control subjects. And when you do it at scale across the population level, we actually see the attention of the model actually focus on different sleep stages. And especially like for PD, we're more focusing on the sleep onset period and the awake period. And this is actually supported by the literature where people have observed this slowing wave of Parkinson's disease in their resting awake period. So yeah, happy to talk more about this. Okay, cool. So let's move on. And so in the first part, we basically see, okay, how sleep actually derive interesting biomarkers for disease. And in the second part, and more recently, our lab has been focusing on building foundation models for human sleep. And using a foundation model approach, it can unlock many other predictions beyond just Parkinson's and can do diverse downstream tasks without training task-specific models. So this work is a collaboration with Ravi Rajesh Wei from UCLA and driven by my students, Zitao and Zongzhe, who did great jobs on modeling sleep. So first, I'd like to start with a brief discussion on why should we build a foundation model. So if you revisit the trend of machine learning over years, we first have classical machine learning models such as SVM or decision tree. And usually they work pretty well when you have very low, very small amount of label data. But because of the parameter size limitations, once you have more and more data, it will hit plateau because of their inherent limits in their number of parameters. And later, in the around 10 years ago, with the flourishing of deep learning field, we actually discovered, okay, we can actually have more and we have like deep networks by stacking more and more layers with increased number of parameters. And these models usually suffer from very low data regime. But when you increase the data amount, it actually, the performance is actually better and better. So foundation model, the key idea of foundation model is when we have access to a huge amount of unlabeled data, that is when we have access to a lot of data that without these clinical outcome labels, for example, for wearables, for rings, or even for your for a lot of other modalities, we collect this unlabeled data from the population level, from the population. And once we adapt this foundation model to a specific cohort, we don't need a lot of amount of labeled data. We can make it, we can make the best of both worlds, basically beating both of these methods. And in reality, we actually have access to a lot of unlabeled data, especially in this mobile human physiological sensing domain, where we can collect this data from very large and high resolution populations, and it is pretty diverse. And in turn, when we want to study specific disease or outcomes, we can collect specific clinical cohorts or study data sets that are much more sparse and restricted, but we can leverage the power of pre-training to adapt them effectively to these specific cohorts. And usually in reality, this is much, much smaller compared to unlabeled data. So we want to apply this philosophy in sleep domain. And recently we built this sleep foundation model. We call it Open Sleep Foundation Model, or OSF in short. So during human sleep, we actually have the synchronized collection of not only the breathing signal, which we mentioned earlier, but also your brain EEG signals, your cardiac activity, such as ECG, and also your muscle movements, such as EMG, etc. But when we take a closer look at the real-world sleep studies, what we found is that it does not necessarily have all the channels at the same time. For example, for headband study, where you usually have access to only a headband, that measures your brain activity, but not the other channels. And in sleep disorder studies, you usually often just measure your cardiac activities and your respirations. And in sleep macroarchitecture studies, we don't measure respirations, but the other channels. And in home studies, you typically just measure respirations, such as what we mentioned earlier. So the key question here is, how can we build a foundation model that can actually generalize to all these patterns so that it can be deployable in different sleep studies? So what we built here is a pipeline that actually works for all these studies. So let's say given an input sequence of the physiological measurements across different channels. What OSF did is we can randomly mask different parts and even an entire channel for different measurements. And then we adopt a teacher-student network where the student wants to match its embeddings or global predictions as the teacher network. And these models are trained in a fully self-supervised manner, which means we don't need any outcome labels such as sleep, staging, or etc., or disease information to train this model. And once this model is trained, and by the way, I'm happy to dive into details, but I will just skip this for the sake of time. And once this model is trained, we'll just freeze this whole backbone. And once we have a downstream label study, we'll just attach a linear head, perform the downstream performance. So, so to support the whole community building, along with the model, we also propose a benchmark called Sleep Bench, which is a large collective and living benchmark by integrating existing public resources and standardizing them. So to train the model, we actually collect 9 data sets, and this results in a total of more than 100,000 hours of sleep recordings, and this is fully public and open source. And we intend to make this as a resource for the community, so we try to make it as a living benchmark, where we're going to incorporate more data from different public resources such as PhysioNet, NCLR, and BDSP. And we also welcome the community contributions to help build this initiative. So one key thing for foundation model is whether it actually scales when you have more data and more compute. So making an analogy to the original scaling law proposed by OpenAI when they trained their GPT model, what they found is with increased compute data size or parameter size, we can see this pretty nice linear relationship of the testing laws. And if you take a closer look, this is actually in log space. And we also validate the same idea, whether that emerged in the sleep studies. So what we did is very similar. And on the y-axis is the sleep staging downstream accuracy. And the x-axis, we vary one aspect each time, whereas have more training steps, have more data size, and also model size. And we observe the same trend. Basically, it scales pretty nicely with increased compute data and model size. And this tells us that as we collect more and more data in this space, we're not saturating or hitting a plateau. And this model will be improved with increased data amount. So once we have this model pre-trained on large-scale data, we can adapt to specific studies with specific label outcomes. And in this study, we mainly focus on 2 evaluation settings. The first one is sleep analysis, which is identifying sleep staging, hypopnea, apnea, or other oxygen desaturation events. And the second setting is to predict future disease based on 1 night of sleep. So in sleep analysis, we basically compare to state-of-the-art pre-training methods, as well as state-of-the-art sleep foundation models. So across different tasks, such as sleep staging, arousal, hypopnea prediction, oxygen desaturation, or central apnea prediction, this model shows pretty competitive results and also is very label efficient. In addition, we also identify pretty promising results on disease predictions. So recall that on the first part, we briefly touched on predicting Parkinson's. And in this part, once we have this sleep foundation model, we actually adapt to very different disease outcomes based on patients' EHR data. And we show that this model prediction is actually more robust and generalizable compared to existing state-of-the-art sleep foundation model across many diseases. And the most interesting part for this model is that it can actually generalize to different studies. So as we motivated earlier, for different real-world studies, you don't actually have the full observation of all the data. And we show here across the 4 aforementioned studies and on 2 representative tasks, arousal prediction and hypopnea prediction, the model actually have higher prediction power and accuracy compared to state-of-the-art sleep foundation models. And in addition, we also try to ask another question. So can we actually connect sleep data with natural language? So very similar to what we have been doing with Evelyn here and also with Google researchers on sensor data. Here we ask another question is, for these dense physiological signals, can we actually connect it with language so that it can enable new capabilities on sleep understanding? For example, generating sleep reports, doing zero-shot predictions, or doing these zero-shot retrievals between this dense physiological data and natural language prompts. So to enable this capability, we formulate this captioning pipeline in an automatic way where we have these channel-specific captions to describe the channel statistics, as well as these local captions where we describe events that actually happen and annotated by specialists within these sleep recordings, as well as these global captions, which describe the actual high-level context about this sleep period, such as what sleep staging it is, and also some individual level labels. And to train this model, we propose another pre-training method, which we call reconstructive contrastive captioner, or ReCoCA in short. So the whole idea is we have specific encoders for both sleep and language, and we enforce 3 losses simultaneously. The first one is a contrastive loss, which aligns these 2 modalities between sleep and language. The second one is a captioning loss, which we have the description for this specific sleep data. And the third one is the reconstruction loss, which is for these high-dimensional and dense physiological signals. We want to preserve this capability of reconstructing from this lower dimensional imbalance. And this actually recovers existing pre-training or multimodal pre-training architectures, such as CLEAP, CAP, and COCA. So this sleep language model actually enables very interesting downstream applications. For example, now we can do zero-shot prediction just using a natural language prompt. And we compare here this model versus fine-tuned LLMs such as Queen and Lava, as well as this private state-of-the-art LLMs such as DeepSeek and Gemini. And across different sleep tasks, we see this model actually bring pretty significant gains, and it's also pretty consistent. And another capability for this model is we can also enable this searching capability by just inputting a natural language prompt and with a database of sleep signals and vice versa. For example, we show here one episode of the sleep signals where there's a REM sleep pattern and the oxygen desaturation events is documented from here to here. We further plot the similarity ranking by retrieving this across a set with 200 sleep episodes. And what we retrieve based on similarity score is pretty consistent in its semantic meanings. For example, for higher ranking or for higher similarity, for examples with higher similarities, we actually see that the semantic meaning is actually matched with the ground truth descriptions. And as the similarity goes down, we gradually see this very nice trend of the semantic similarity, where this one is partially correct and this one is completely irrelevant. And finally, this model also supports this sleep caption or sleep report generation. And we compared it qualitatively with existing state-of-the-art LLMs, and which is also fine-tuned on the same sleep datasets. So what sleep LLM does is pretty robust, and we can view the prediction or the generation is actually highly correlated and even correct compared to this ground truth. And briefly mention the same part, which we did at Google, and is actually led by Evelyn Zhang in here. We also have this idea of connecting natural language with our wearable data and not just sleep data. So similarly, we have this capability of generating the descriptive text for wearable data, such as Google Fitbit. And what we have tested is this model is pretty generalizable to different versions of devices. And now we're extending it to more broader consumer health domains. Okay, I'll also stop here for a while and happy to take any questions about this part. Okay, awesome. So I'll quickly go over the last part. So so here we want to see whether, given this like dense physiological signals, we have been talking about foundation models or specific deep learning models, and we want to see whether existing large language models can help us understand these signals, or does it really work on such signals? And this is a collaboration with Emma, Daniel from Google, and Wei from UCLA, and led by my students, Ray and Hee. So going back to the very initial figure I plotted, we have so many different health and physiological time series coming from different domains. For example, this is the CGM across the day, and this is one piece of breathing signals. This is an example of the sensor data, and this is an example of physiological time series for sleep. So as you can see, they span different frequency ranges, they have different length, they also have this very different behaviors across time. So we ask, can LLMs actually reason over this health time series? So to answer this question, we propose this benchmark called HEARTS, and in short, is health reasoning on time series. And we hope to collect a resource for the community that actually cover the most broadest setting across day. For example, we have collected 20 signal modalities, and this span over 12 domains, such as sleep, surgery, motion, metabolic, etc. And across these domains, the signal property is actually have one of the most broad coverage across both sequence length, across the sampling frequency, as well as the time span. And finally, by reasoning, we define 4 categories for measuring its performance. The first one is perception, which is how good or how bad the models can do in terms of data science tasks. And the second one is inference. So how can we, for example, one example is how can we localize anomaly events based on this input? And we also have this generation/forecasting task, as well as this deduction task, which is more higher level reasoning capabilities. For example, can we identify which segment of the data happened first? And again, we position this work with existing benchmarks and hope it to be the most broadest coverage and a living resources for the community. We also built a leaderboard for this. So we have tested more than 10 existing state-of-the-art LLMs, and the leaderboard is updating every month. So some interesting findings. So the first one is we actually plot the performance of these large language models with respect to their intelligence index. So you can view this intelligence index as a general intelligence capability assessed over many domains such as finance, coding, math, etc. So this is the most up-to-date intelligence assessing method. And on the y-axis is the overall score on our benchmark hearts. And what we found is very interesting. So although there's a difference across these models on the intelligence index, it is actually very weakly correlated with their performance on physiological signal reasoning. And we further plot this against so-called state-of-the-art models or human baselines across different tasks. And again, this is not a strict comparison, but just give you a sense on how large the gap it is right now. So across different tasks and domains, clearly LLMs still lag behind either human experts or state-of-the-art models. And specifically, when we look into the performance with respect to sampling frequency and also the sequence length, we find this inverse correlation. That is, LLMs tend to perform poorly on longer sequence, as well as signals with higher sampling frequencies. And this clearly shows a gap in the LLM reasoning for physiological time series. And we hope this will serve as a foundation for further testing, evaluating, and building more powerful models that can understand and reason over health time series. All right, so to quickly wrap up this talk, let's talk about some future directions in this space. So I like this illustration very much. And when you touch, for example, in this illustration, when you touch different parts of the elephant, you have different imaginations on what you're actually guessing. I think this is very similar to what is the landscape in healthcare and medicine. So for one modality we measured, we can usually infer some properties of the person's health. But to give a complete picture, we do need to integrate multiple sources, multiple sensing sources, genetics, imaging, etc., to give a full picture. And as a first step, we built these personal health agents that actually have dedicated agentic frameworks and integrate the personal health data from different domains. And by this, so this again is a research prototype, but by building this pipeline, we hope to have a way that can actually integrate multimodal data and help the users understand their health in a more informed way. Okay, so given the time limit, I'll probably just skip over the last part. And again, before I end this talk, shout out to my students and all the collaborators, and they are the ones who did the hard work. All right, so thank you very much. I'm happy to take more questions.
Thank you. Any questions online? If people want to chat, messages in the chat, I can read them out. And if people are in the room and have questions, they can raise your hand. We're about 5 minutes. I have a question online. So, how do you design a contrastive learning objective when your positive pairs a structurally different feature space and the missingness pattern itself carries semantics meaning? You can probably see the
sure.
message if you want.
Yes.
To read it somewhere in the chat.
Oh, yes.
Oh, yes, over there.
Yeah, thank you. Sure. So I believe you're referring to the sleep foundation model part. Is that correct? Let me localize that slide. Cool. So, so the question is, how do you design a contrastive learning objective? Okay. So here's the omitted details. So this objective is not only contrastive, but a combination of contrastive and reconstructive. So if you have a sense of literature on Dino, this is pretty much like the Dino objective, where you have this contrastive methods, but also you're trying to reproduce the global feature from one to the other. So I think this method actually have the best of both worlds. And what we observe empirically is it actually generalizes better compared to a single contrastive objective. And to your question, I think, no, we don't actually need positive pairs because these two are actually from the same input. Does that answer your question? Okay, thank you.
Okay, great. Any other questions? There's a question.
Yeah, go ahead.
Regarding the same work, you also told that predicts patient level disease prediction. So with the huge high dimensional data of overnight recording, how do you narrow down that to patient level disease detection, like the ones that example that you gave that diabetes?
So your question is, how do we select the disease for disease prediction evaluation?
So you have this high dimensional data of 10 to 9 hours of sleep data.
Yep.
From there, you're going to again time for binary decision
Yes.
of whether the disease exists in the patient body.
Yep.
So how do you do that?
Oh, okay. So the question is, how does this model actually work for disease prediction, right? So so it goes back to the in general, like how does foundation model works? So basically, once you have this pre-training done, usually like you have a very dense, very large number of encoding layers. And what we did is once the pre-training is done, like during pre-training stage, we don't need any label information. We just do like unsupervised or self-supervised learning. And then when you have specific study data sets, for example, one predicts certain diseases, for example, and that will have a very small number of participants and limited number of data. And what we do is we basically just do this fine tuning on top of the encoder. So the whole encoder is freezed. So you can see like this part is actually like trained with very light network. Yeah.
Thank you.
Awesome.
I don't see any other question. Maybe I can ask a final question of
For sure.
there's a discussion generally about foundation models and LLM, wearable foundation model, as you and I perhaps call them, and then the LLM modeling. And I guess with your Google hat, my question is, will we see essentially all of this being swollen by what people would call LLM? Would LLM evolve into covering all of this without this, we feed this textual part and the time series part? Where do you see this going?
Yeah, that's an excellent question. And I have a lot of thoughts actually, but I think in short, it's an open question for the community, but that also depends on how you view this wearable data, this specific physiological modality. Like, is it similar to vision and audio that already been incorporated, or it has certain structures that you need new designs? And I don't have a specific answer to that, but my belief, or right now at this point, I tend to believe we need a new structure for modeling, for effectively modeling physiological time series. So one example is what we showed in this benchmark, that current LLM training, although they're not trained specifically on this data, they cannot really reason about these signals. And I believe time series actually have its specific structure. For example, it's sequential, it's high, it has a frequency component. And maybe we need some new architecture or new pre-trained objective that can well handle this type of data beyond just transformers and how you handle language. But to your question, Cecilia, I think, no, I don't have a definite answer.
Your example of video is a good one. I wonder if these models have been trained on large videos. That's my thing.
Yeah, exactly.
And it's just maybe they haven't trained on this.
Yes,
I don't know.
yes. There's always like a bitter lesson in the field, like whether it's scaling or versus given projects.
Well, thank you for the amazing talk, and thank you to the audience, and thank you.
Thank you very much.